Hello and welcome to Later Night Space. Before settling in, take a quiet moment to like the video and subscribe to the channel. It helps this small, calm corner of the universe reach other nighttime listeners who are also looking for something thoughtful and unhurried. And if you feel like it, leave a comment letting everyone know where you're watching or listening from tonight. Tonight's question is deceptively simple. Will the universe ever stop expanding? Right now, as you sit here, space itself is stretching, not just between distant galaxies, but everywhere, quietly and continuously. The Milky Way is drifting away from galaxies far beyond it. Clusters of galaxies are separating. Light traveling across billions of years is being gently stretched along the way, its wavelengths lengthening as the universe grows larger. And yet, nothing in your room appears to be expanding. Your walls are not drifting apart. The earth is not swelling beneath your feet. The atoms in your body remain firmly bound together. On human scales, everything feels stable, still, contained. But on cosmic scales, something extraordinary is happening. For most of human history, the universe was imagined as static and eternal. Even Albert Einstein initially believed it must be unchanging. When his own equations suggested otherwise, he adjusted them to preserve a stable cosmos. It was only in the early 20th century, through the work of astronomers like Edwin Hubble, that the evidence became undeniable. The universe was not standing still. It was expanding. At first, scientists assumed gravity would eventually slow this expansion down. After all, gravity pulls matter together. Surely, over enough time, the combined mass of all galaxies would act like a cosmic brake. But then, near the end of the 20th century, something even stranger was discovered. The expansion is not slowing, it is accelerating. That single revelation transformed our understanding of cosmic destiny. It suggested the presence of something unknown, something now called dark energy, pushing space itself outward. So the question becomes deeper. If the universe is expanding and expanding faster over time, is there any mechanism that could bring it to a halt? Could gravity ever regain control? Could expansion reverse? Or is the cosmos committed to growing larger forever? This is not just a question about distant galaxies. It is a question about the ultimate fate of everything that exists. Stars, planets, black holes, atoms, light itself. The answer determines whether the universe ends in collapse, in freezing silence, or in something stranger still. Over the next while, attention will drift outward, past nearby stars, beyond the edge of the Milky Way, through the deep cosmic web, tracing the evidence, the equations, and the quiet uncertainties that shape modern cosmology. The universe is vast, patient, and still full of unanswered questions. And tonight, one of the biggest waits quietly in the dark. Will it ever stop expanding? The first strange thing about that question is how quickly it pulls the mind away from everyday life. Space feels like the ultimate background, the place where everything happens but which never changes. It looks calm, it looks fixed. The stars keep their patterns. The sky returns each night like a familiar ceiling. And for most of human history, that impression shaped the deepest assumptions people made about the cosmos. The universe was treated as permanent, steady, and essentially unchanging. A grand stage where events unfolded, but where the stage itself remained still. That assumption was not foolish. It was reasonable given what the naked eye can see. Even early telescopes suggested an orderly heavens, not a living, evolving space-time. A static universe fit the intuition of permanence. It also fit the philosophical desire for something solid beneath the chaos of human history. But then physics began to do what it often does at its best, which is to gently ruin a perfectly good intuition. In the early 20th century, Albert Einstein arrived with a new way to think about gravity. In 1915, his theory of general relativity replaced the old idea of gravity as a force acting instantly across distance. In Einstein's view, gravity is the curvature of space-time. Mass and energy shape the geometry of space-time, and that curved geometry guides the motion of matter and light. A planet orbits a star not because it is being tugged by an invisible string, but because it is following the straightest possible path through a curved space-time. Light bends near a massive object because space-time itself is bent there. Gravity becomes less like a pull and more like a shape. When Einstein applied his new equations to the universe as a whole, he discovered an uncomfortable implication. A universe filled with matter does not naturally sit still. Under broad, reasonable assumptions, the equations suggest that space-time should evolve. It should either expand or contract. In other words, the universe should change its size over time, not in the sense of growing into an outside emptiness, but in the sense that distances within the universe should be different tomorrow than they are today. This did not fit the scientific mood of the time. The universe was widely assumed to be static. To preserve that assumption, Einstein introduced an additional term into his equations, called the cosmological constant. Its effect was to provide a kind of repulsion that could balance gravity on the largest scales. In a universe where matter pulls inward, the cosmological constant could push outward. With the right tuning, the universe could be held in a delicate equilibrium, neither expanding nor contracting. Even if that adjustment produced a static solution, the deeper message remained. The equations were trying to say that stillness was not the default. Stillness had to be carefully engineered. In the early 1920s, Alexander Friedmann examined Einstein's equations without forcing the universe to remain static. Friedmann found a family of solutions in which the scale of the universe changes over time. Depending on the total energy density, a universe could expand forever, expand and slow, or expand and eventually recollapse. Friedmann's work was purely theoretical, but it showed that an evolving universe was not a quirky edge case. It was an expected outcome of general relativity. Soon after, Georges Lemaitre arrived at similar conclusions, independently deriving expanding universe solutions. Lemaitre also took a bold step further. If the universe is expanding now, then in the past it must have been smaller, denser, and hotter. He proposed that the universe once existed in a compressed state, something like a primeval atom, and that expansion followed from that early condition. This line of reasoning helped lay the groundwork for the modern Big Bang model, a universe with a history rather than a timeless steady state. At this point, the expanding universe was a beautiful mathematical possibility. But mathematics alone is not enough. Nature must agree. That agreement began to appear through astronomy. In 1929, Edwin Hubble published observations that changed cosmology permanently. Working at the Mount Wilson Observatory in California, using the 100-inch Hooker telescope, Hubble studied distant galaxies and compared their distances with the spectral shifts in their light. Many of these galaxies showed redshift, meaning their light was shifted toward longer wavelengths. More importantly, Hubble found a pattern. The more distant a galaxy was, the greater its redshift tended to be. From this, Hubble derived a simple proportional relationship that now carries his name. In clear English, it can be said as recession speed equals the Hubble constant multiplied by distance. The farther away a galaxy was, the faster it appeared to be receding. This was not a small tweak to a comfortable worldview. It implied that the universe was not static. It was expanding. There is a subtle trap here, and it is one that the human mind falls into easily. Expanding can sound like an explosion. It can sound like galaxies are firing outward through space from some central point. That picture is understandable, and it is also wrong in an important way. The expansion of the universe is not primarily galaxies moving through space like shrapnel. It is space itself stretching, so that the distance between galaxies increases, even if they are not actively propelling themselves away. A familiar analogy helps as long as it is handled gently. Imagine raisin bread rising in an oven. As the dough expands, the raisins move apart. Each raisin sees the others receding. There is no special central raisin that everything flees from. The expansion is built into the dough itself. In cosmology, galaxies are like raisins and space-time is like the dough. The motion is largely the growth of the space between objects. The analogy has limits. Raisin bread expands into surrounding air. The universe does not expand into an external space because general relativity does not require the universe to have an outside. Expansion is not the universe pushing into emptiness. It is the change of distances within the universe, described by a changing scale factor in the mathematics of cosmology. If there is something outside the universe, physics does not currently require it. An observation cannot test it. So what does it mean physically for space to stretch? In cosmology, the large-scale universe is often described using the Friedmann-Lemaitre-Robertson-Walker metric, which is a way of representing a universe that is homogeneous and isotropic on large scales. Homogeneous means it looks roughly the same in every region when averaged across vast distances. Isotropic means it looks roughly the same in every direction. Under these assumptions, expansion is a change in the scale factor, the number that tells how distances between far apart, unbound objects evolve over time. This brings up another point that needs to be stated clearly, because it stops a great deal of confusion before it begins. Expansion does not pull everything apart. It does not stretch people, planets, or atoms. It does not slowly widen the gap between the floor and the ceiling. The reason is simple in principle. Local forces overwhelm cosmic expansion on small scales. Within the Milky Way, gravity binds stars into a rotating galaxy. Within the solar system, the sun's gravity holds planets in their orbits. Within Earth, electromagnetic forces hold solids together. Within atoms, electromagnetism binds electrons to nuclei. These forces are enormously stronger than the effect of cosmic expansion at small distances. Expansion is detectable only when comparing distances across scales where gravity does not bind systems together, typically millions of light years and beyond. A useful way to phrase it is that there are two kinds of distance in play. There is the distance between objects that are gravitationally bound, like stars within a galaxy, where the system's internal gravity dominates. Then there is the distance between objects that are not bound, like widely separated galaxies, where the overall expansion of space-time becomes the main driver of their increasing separation. This is why the Milky Way is not being stretched apart by expansion, and it is also why, at the larger scales, the universe can expand while still allowing local structures to exist. Now consider what happens to light traveling through this expanding space-time. Light is a wave. It has a wavelength, the distance between peaks. In an expanding universe, as light travels, the space it travels through stretches. The wavelength stretches with it. This is cosmological redshift. It is different from a simple Doppler shift, which is caused by an object moving through space. Cosmological redshift is caused by the expansion of space itself. The light wave is lengthened by the growing space-time it crosses. This is not merely a poetic idea, it is measurable. Spectral lines from distant galaxies shift toward longer wavelengths in a way that matches expanding universe models. Light emitted in the visible range can be stretched into the infrared. Microwave background photons emitted when the universe was much hotter have been stretched into microwaves by expansion, which is part of why the cosmic microwave background radiation exists at such a low temperature today. To quantify expansion in the present era, astronomers use the Hubble constant. A common modern value is on the order of 70 kilometers per second per megaparsec. A megaparsec is roughly 3 million light-years. Put plainly, for every additional 3 million light-years of distance, the recession speed increases by about 70 kilometers per second. At a distance of around 100 megaparsecs, the implied recession speed is around 7,000 kilometers per second. These are strange speeds because they are not the usual kind. They are not the speed of a spaceship moving through space. They are the speed at which distance increases due to expanding space. At extreme distances, this can even lead to recession speeds that exceed the speed of light without violating relativity, because relativity limits the motion of objects through local space-time, not the growth of distance created by the expansion of space-time itself. This is where it becomes important to stay grounded. Expansion is a global property of the universe. Locally, physics behaves normally. The speed of light remains the speed limit for motion through space. But globally, space-time itself can evolve so that distant regions separate faster than light could cross the growing gap. The question then becomes, how does anyone measure these enormous distances in the first place? Astronomy cannot use a tape measure across space. Instead, it builds a distance ladder, a sequence of methods that calibrate one another. One of the most important early steps on this ladder involves Cepheid variable stars. In the early 20th century, Henrietta Swan Leavitt discovered a relationship between the period of a Cepheid's brightness variations and its intrinsic luminosity. In everyday language, the rhythm of its pulsing reveals how bright it truly is. Once true brightness is known, comparing it to how bright the star appears from Earth gives a distance. Cepheids allow astronomers to measure distances to nearby galaxies. But to reach deeper into the universe, brighter markers are needed. This is where Type 1 supernovae become essential. A Type 1 supernova occurs when a white dwarf in a binary system gains mass from a companion star and approaches the Chandrasekhar limit, about 1.4 times the Sun's mass. At that threshold, electron degeneracy pressure can no longer hold the star up against gravity, and a thermonuclear runaway disrupts the white dwarf in a catastrophic explosion. Because these explosions happen under similar conditions, their peak brightness is fairly uniform, making them excellent standard candles for measuring distances across billions of light years. Space-based instruments improve these measurements by escaping the blurring and absorption of Earth's atmosphere. The Hubble Space Telescope has played a major role in refining the distance ladder, especially through its careful observations of Cepheid variables and supernovae in host galaxies. There is also a second, independent way to infer the expansion rate by studying the early universe directly through the cosmic microwave background radiation. Satellites such as the Planck mission have measured tiny fluctuations in this background with exceptional precision. By fitting those patterns to cosmological models, scientists can infer the expansion history and derive a value for the present expansion rate. Here is where modern cosmology reveals a small but persistent puzzle. The expansion rate measured using the local distance ladder, involving Cepheids and Type 1 as supernovae, tends to be somewhat higher than the expansion rate inferred from the cosmic microwave background. This mismatch is known as the Hubble tension. It may arise from subtle measurement systematics that are still being chased down, or it may hint at new physics, perhaps involving early universe processes, neutrino behavior, or a more complex form of dark energy than a simple cosmological constant. At present, the tension remains unresolved, and that uncertainty is one reason cosmologists speak carefully about the details, even when the broad picture is clear. And the broad picture is clear. The universe expands. The expansion is measured through cosmological redshift. Its present rate is quantified by the Hubble constant. The concept is grounded in general relativity and expressed through the changing scale factor of space-time. Local structures remain intact because binding forces dominate on small scales. On large scales, the expansion shapes the universe's history and will shape its fate. All of this brings the original question into sharper focus. Will the universe ever stop expanding is not a question about whether galaxies are moving. It is a question about the evolution of the scale factor, about how the expansion rate changes over time, and about what the universe contains that could slow it down, speed it up, or alter it entirely. The universe is expanding now. That much is established beyond serious doubt. The remaining uncertainty is not whether expansion exists, but whether expansion is being slowed, sustained, or driven. That is where gravity, energy density, and the deep contents of the cosmos take over the story, with consequences that play out across distances measured in billions of light years and times measured in billions of years. Once the idea of expansion is clear, the universe starts to feel less like a place and more like a process. Space is not merely the stage where events unfold. Space is one of the things that is unfolding. And when something is unfolding, the next step is always measurement. Not a vague sense that it is happening, but a number that can be tested, compared, argued over, and refined until it becomes stubbornly real. That number is often introduced as the Hubble constant, but it helps to think of it as the present-day value of the expansion rate, because the expansion rate changes over time. In cosmology, the broader concept is the Hubble parameter, which evolves as the universe evolves. The constant label survives mostly because it is a constant at any given moment in cosmic time, not because it is constant across the history of the universe. The starting point remains the same statement in clear English. Recession speed equals the Hubble constant multiplied by distance. The challenge is that both sides of that statement must be measured in the real universe. Redshift gives a handle on recession, but distance is the hard part. Space offers no ruler, and galaxies do not come with price tags that say how far away they are. So astronomers built a system that is equal parts cleverness and patience: the cosmic distance ladder. The distance ladder works by stitching together several methods, each reliable within a certain range. The first steps are local, close enough that geometry can help. Stellar parallax, the apparent shift of a nearby star against a distant background as Earth orbits the Sun, provides distances to nearby stars. That baseline, 1 astronomical unit, is tiny on cosmic scales, but it is enough to anchor the first rung. The next rung relies on stars that behave in a predictable way. Cepheid variable stars brighten and dim with a regular period, and their pulsation period is linked to their intrinsic luminosity. Henrietta Swan Leavitt discovered this relationship while studying Cepheids in the Magellanic Clouds. In everyday terms, a Cepheid's rhythm reveals how bright it truly is. Once true brightness is known, comparing it to apparent brightness gives distance. Cepheids are bright enough to be seen in nearby galaxies, which is exactly what makes them so valuable. They allow astronomers to step beyond the Milky Way and begin mapping the local universe. But Cepheids still have limits. To reach billions of light years, the ladder needs something brighter, something that can briefly outshine an entire galaxy. That is where Type 1 a supernovae enter the story, with a kind of awful usefulness. A Type 1 a supernova is not simply a star exploding because it ran out of fuel. It is typically a white dwarf in a binary system gaining mass from a companion. As it approaches the Chandrasekhar limit, about 1.4 times the mass of the Sun, electron degeneracy pressure can no longer support it. The white dwarf undergoes a thermonuclear runaway that disrupts it completely. The explosion is bright enough to be seen across enormous distances, and the peak brightness is consistent enough that, after careful calibration, Type 1a supernovae function as standard candles. This is the heart of the distance ladder's power. Cepheids calibrate distances to nearby galaxies. Those calibrated galaxies host Type 1a supernovae. The supernovae then extend distance measurements far deeper into space, allowing redshift and distance to be compared across much of the observable universe. The Hubble Space Telescope plays a quiet but crucial role here. From orbit above Earth's atmosphere, it can measure Cepheids and resolve crowded star fields with far less distortion. Observations from Hubble have been central to refining the distance ladder and improving the precision of the local expansion rate. But cosmology rarely trusts a single method, especially when the stakes are the fate of the universe. So there is another major way to infer the expansion rate, one that does not rely on nearby calibrators at all. It looks backward to the early universe and uses a relic signal that has been traveling through space since the cosmos was young. That signal is the cosmic microwave background radiation. It is the afterglow of the early hot universe, dating to roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen in a process called recombination. Before recombination, photons scattered constantly off free electrons, keeping the universe opaque like the interior of a star. After recombination, photons traveled freely, and those photons are still traveling today, stretched into microwaves by expansion. Space missions such as COBE, WMAP, and the Planck satellite measured tiny temperature fluctuations in this background radiation. These fluctuations are not random noise. They are a map of early density variations, and they contain geometric information. By fitting the observed pattern of fluctuations to a cosmological model, scientists can infer the values of key parameters, including the expansion rate. Here, the universe reveals a small, persistent tension. The expansion rate inferred from the early universe using the cosmic microwave background tends to be lower than the expansion rate measured locally using Cepheids and Type 1a supernovae. This discrepancy is called the Hubble tension. It is not a minor annoyance because it survives careful checking and improved data. It could still be explained by subtle systematics in measurement, but it could also hint that the standard model is missing something, perhaps a small feature in the early universe or a component that behaved differently when the cosmos was young. Even with this tension, the essential point stands firm. Expansion is not only observed, it is quantified. It has a measured rate. It has an evolving history. And once there is a measured history, the question becomes more precise. What determines that history? What controls whether the expansion slows down, stays steady, or speeds up? This is where gravity enters the story in its most cosmic form, not as the force that keeps feet on the ground, but as the geometry that shapes the universe's overall evolution. In general relativity, the expansion of the universe is described using the Friedmann equations, derived from Einstein's field equations by Alexander Friedmann, and later developed further in the context of Georges Lemaitre's work. The Friedmann equations describe how the scale factor changes with time, based on the universe's total energy density, pressure, and curvature. They are not merely mathematical ornaments. They connect what the universe contains to what the universe does. One of the most useful quantities in this framework is critical density. Critical density is the average energy density required for the universe to be spatially flat. In clear English, the critical density can be described as critical density equals 3 multiplied by the square of the expansion rate divided by 8 multiplied by pi multiplied by the gravitational constant. The exact form matters less than the meaning. If the universe's total density is greater than the critical density, geometry becomes positively curved. If it is less, geometry becomes negatively curved. If it equals the critical density, geometry is flat. This might sound like an abstract geometry lesson, but geometry in cosmology is destiny, because density controls gravity's ability to slow expansion. In a universe filled only with matter and radiation, gravity acts to decelerate expansion. Matter has energy density and negligible pressure on cosmic scales, while radiation has energy density and positive pressure. Both contribute to gravitational attraction in the Friedmann equations. As the universe expands, matter density dilutes because the same mass spreads over a larger volume. Radiation density dilutes as well, and additionally, the radiation's wavelength stretches, reducing energy further. This simple fact means that the universe evolves through eras. In the earliest times, radiation dominated. Later, matter dominated. And in those eras, gravity should cause the expansion rate to decline over time. Expansion would continue, but it would slow, like a ball thrown upward that never quite stops, but steadily loses speed. For much of the 20th century, this was the expectation. If the universe had enough matter, gravity might even halt expansion and reverse it. The universe could recollapse in a big crunch. If it had too little matter, it would expand forever, gradually slowing toward a cold, dilute future. The problem was to determine which fate applied, and that problem reduced to a cosmic accounting question. How much mass and energy does the universe contain? Early inventories were discouraging. If only visible stars and gas were counted, the universe seemed too light. There was not enough gravity to slow expansion much, let alone reverse it. This is where the dark matter problem, already hinted at by Fritz Zwicky and later sharpened by Vera Rubin's galaxy rotation curves, became essential. Dark matter adds mass without adding light. It deepens gravitational wells, shapes galaxy formation, and increases the total matter density of the universe. But even with dark matter included, matter appeared to account for only a fraction of what would be needed for recollapse in the simplest models. In a matter-dominated universe, the expansion history is sensitive to the density parameter, the ratio of actual density to critical density. If that ratio is above 1, recollapse becomes possible. If it is below 1, expansion continues forever. If it equals 1 exactly, the universe is flat and expands forever while slowing. In the matter-only case. This is why cosmologists became obsessed, in the most professional and respectable sense of the word, with measuring density and curvature. These were not details. These were the numbers that would decide whether the universe is headed toward collapse or endless expansion. The cosmic microwave background provided a new way to measure curvature directly. The pattern of fluctuations includes a characteristic physical scale set by sound waves in the early plasma, sometimes described as baryon acoustic oscillations in a broader context. When that scale is projected onto the sky, its apparent angular size depends on the geometry of space-time. If the universe is positively curved, the scale appears larger. If negatively curved, it appears smaller. Measurements from WMAP, and especially Planck, indicate that the universe is very close to flat. Flat geometry is an elegant result, but it also sharpens the mystery. Flatness implies that the total energy density is very close to critical density. Yet matter, including dark matter, does not appear to supply the full amount. Something else must be present to bring the total up to critical density, or the universe would not appear so flat in these measurements. This is where pressure becomes important in a way that feels counterintuitive. In everyday life, pressure pushes outward, so it seems like pressure should fight gravity. In general relativity, pressure contributes to gravity. Positive pressure increases gravitational attraction. That is why radiation, with its positive pressure, gravitates more strongly than matter alone would suggest. But general relativity also allows something stranger: negative pressure. And negative pressure can produce a repulsive gravitational effect that accelerates expansion. This is not introduced here as a dramatic twist, but as a logical consequence of the equations. The Friedmann equations do not only ask how much energy exists, they also ask what kind of pressure that energy has. If the pressure is sufficiently negative, the expansion can accelerate rather than decelerate. At this stage of the story, it is enough to hold the concept gently. The universe's expansion history is not determined solely by matter pulling inward. It is determined by the total energy density and the pressure associated with each component. Matter dilutes. Radiation dilutes faster. Curvature becomes less important as the universe grows, and a component with the right kind of pressure can change the entire future. For a long time, cosmologists still expected deceleration because matter and radiation were the familiar ingredients. The job was to measure that deceleration. Observational programs were built to detect it. The most promising tool was already sitting in the distance ladder itself. Type 1a supernovae, bright enough to be seen far back in time, allowing astronomers to compare how the expansion behaved in the past with how it behaves now. If gravity from matter was slowing expansion, the supernova data would show it. If the universe had been expanding faster long ago and slowed gradually, distant supernovae would appear slightly different in brightness than they would in a universe with a constant expansion rate. That difference would be the signature of cosmic braking, the gentle hand of gravity acting over billions of years. By the time these measurement programs matured in the 1990s, the universe was about to answer the deceleration question directly. The expectation was not reckless. It was grounded in decades of theory and observation. Gravity had every reason to be in charge of the long-term story, because gravity is what builds structure. But the universe had a habit of being mathematically consistent while still managing to surprise anyone who grew too comfortable. At this point, the universe has already admitted to one unsettling fact: space expands. And once that becomes part of the worldview, a second question rises almost automatically. How did anyone become confident enough to say the universe began hot and dense? And how did anyone learn what the universe is made of in the first place? The answer is that the universe left behind a kind of fossil record, not in rocks or bones, but in light. Long before any galaxy existed in its modern form, the universe was a very different place. It was hotter, denser, and filled with a plasma of charged particles. Electrons and protons moved freely. Photons, the particles of light, were constantly scattered by those free electrons. In that environment, space was not transparent. It was more like the inside of a fog bank or the interior of a star, where light cannot travel far without being redirected. As expansion continued, the universe cooled. Cooling here does not mean heat leaking into surrounding emptiness. It means energy becoming more spread out as space expanded, and radiation losing energy as its wavelength stretched. Eventually, the temperature dropped enough for electrons and protons to combine into neutral hydrogen. This transition is called recombination. It occurred when the universe was roughly 380,000 years old, long before stars, long before planets, long before anything that would look familiar. Once electrons were bound into atoms, photons no longer scattered as easily. Space became transparent. Light could finally travel freely. That freed light is still traveling today. It fills the universe in every direction as a faint glow called the cosmic microwave background radiation. It is the afterglow of the early universe, cooled by expansion from a hot, bright environment into microwaves. Today, its temperature is about 2.7 degrees above absolute zero, which is cold enough to sound like the universe has left the refrigerator door open for a very long time, but still warm enough to be measurable with careful instruments. The discovery of this background radiation in 1965 was not the result of someone pointing a telescope at the early universe and confidently saying, "There it is." It was a more human story. Arno Penzias and Robert Wilson, working at Bell Labs, were using a microwave antenna for communication research. they encountered a persistent noise that seemed to come from everywhere. They checked equipment. They checked the sky. They even cleaned out the antenna, including dealing with pigeons that had made themselves comfortable in it. The noise remained. It was uniform, coming from all directions. It turned out they had detected the relic radiation predicted by Big Bang cosmology. The cosmic microwave background is often described as a baby picture of the universe, which is a nice phrase as long as it is taken seriously. It is not a picture of galaxies. It is a picture of the universe before galaxies formed, when matter was still almost evenly distributed, with only tiny variations in density and temperature. Those variations matter immensely because they are the seeds from which all later structure grew. In the early 1990s, the COBE satellite, operated by the National Aeronautics and Space Administration, measured the cosmic microwave background with enough precision to detect these tiny fluctuations. The variations were small, about 1 part in 100,000. That is like measuring the height of a mountain range on a planet the size of Earth, and finding that the bumps are only a few meters high. Yet those tiny ripples were the earliest visible fingerprints of structure formation. After COBE, the Wilkinson Microwave Anisotropy Probe, usually called WMAP, refined the map in the early 2000s, providing far better angular resolution and more detailed measurements of the fluctuation pattern. Then the Planck satellite, operated by the European Space Agency, improved precision even further. Planck's measurements became one of the strongest anchors for the standard cosmological model, because they allowed cosmologists to infer multiple parameters at once: the universe's age, its composition, and its large-scale geometry. One of the most important results from cosmic microwave background measurements is that the universe appears spatially flat, within a very small margin of error. Flatness here means that on the larger scales, geometry behaves in a way consistent with Euclidean expectations, at least within current measurement limits. Parallel lines do not converge like they would on a sphere, and they do not diverge like they would on a saddle, not in any detectable way across the observable cosmos. This flatness is not just a geometric curiosity. In the Friedmann framework, geometry is tied to total energy density. A flat universe implies that the total energy density is extremely close to the critical density. In other words, when the universe is tallied up in terms of everything that gravitates, the total comes out remarkably close to the value that makes the large-scale curvature nearly zero. That is a stunning piece of information because it suggests the universe is balanced on a cosmic knife edge. It also creates an immediate practical question. If the universe is close to critical density, what is it made of? And can the known ingredients actually add up to that total? The cosmic microwave background does not just hint at density in a vague way. The pattern of fluctuations includes specific features created by sound waves that traveled through the early universe's plasma. These waves left an imprint in the form of peaks in the background's power spectrum, a kind of frequency fingerprint of early physical processes. The precise position and relative heights of these peaks reveal how much ordinary matter exists, how much non-ordinary matter exists, and how the universe's geometry affects the path light takes on its way to observers. When those parameters are extracted, an unexpected accounting emerges. Ordinary matter, the kind that makes stars and planets and people, is only a small fraction of the total. The rest is not luminous in the usual way. And that conclusion does not come from one measurement or one mission. It arises from multiple independent lines of evidence converging on the same answer. Even before cosmic microwave background mapping reached its modern precision, astronomers had encountered a mass problem in a much more direct and almost rude way. Galaxies and galaxy clusters behave as though they contain more mass than can be seen. The first major clue appeared in the 1930s when Fritz Zwicky studied the Coma cluster, a large cluster of galaxies. Zwicky measured how fast the galaxies within the cluster were moving. If a cluster is held together by gravity, the velocities of its galaxies should relate to the cluster's total mass. In a gravitationally bound system, higher internal speeds require more mass to keep objects from flying apart. Using the virial theorem, Zwicky inferred that the Coma cluster must contain far more mass than the visible stars and gas could provide. He proposed that the missing mass was present but not emitting light. He called it dark matter. At the time, Zwicky's suggestion was not widely embraced. Part of the issue was that it sounded like a cosmic excuse. When things do not add up, it is tempting to invent an invisible substance. But the universe has a way of making the same point repeatedly until it becomes exhausting to ignore. In the 1970s, Vera Rubin, working with Kent Ford, measured the rotation curves of spiral galaxies. If most of a galaxy's mass is concentrated in its luminous central regions, then stars farther out should orbit more slowly, in much the same way that planets farther from the Sun orbit more slowly. That is what Newtonian gravity predicts for a mass concentrated toward the center. But Rubin's observations showed that rotation curves were flat. Stars far from the galactic center were orbiting at roughly the same speed as stars much closer in. This implies that mass is not concentrated only in the luminous disk. Instead, galaxies appear to be embedded in extended halos of unseen mass, stretching far beyond the visible stars. This was not a subtle effect. It was dramatic, and it was not confined to one galaxy. It appeared across many spiral galaxies, suggesting that dark matter was not a special quirk, but a general feature of galactic structure. Additional evidence came from gravitational lensing, a phenomenon predicted by general relativity in which mass bends the path of light. Massive objects like galaxy clusters can act like lenses, distorting and magnifying the images of more distant galaxies behind them. By measuring the lensing distortions, astronomers can infer how much mass is present, including mass that emits no light. These lensing maps often reveal mass distributions that exceed the visible matter by large factors, again supporting the existence of dark matter. There are also rare cosmic events that make the separation between visible matter and dark matter especially stark. One of the most famous is the Bullet Cluster, a collision between two galaxy clusters. In such collisions, hot gas, which makes up much of the ordinary matter in clusters, interacts and slows due to pressure and friction. Dark matter, if it exists and interacts weakly, should pass through with minimal resistance. Observations of the Bullet Cluster show that the hot gas visible in X-rays is separated from the dominant mass distribution inferred from gravitational lensing. The Chandra X-ray Observatory has played a key role in observing this hot gas. The simplest interpretation is that most of the mass is in a component that does not collide or radiate like ordinary matter. Taken together, these lines of evidence make dark matter one of the most strongly supported unknowns in modern physics. It is unknown in the sense that its particle nature is not established. It is not unknown in the sense of being optional. The universe behaves as though it is there. This matters for the expansion story because gravity depends on mass and energy. If dark matter adds substantial mass, then it strengthens gravity's ability to slow expansion. For a time, dark matter made it more plausible that the universe might be dense enough to decelerate strongly, perhaps even to halt and reverse, depending on total density and the behavior of other components. But the cosmic microwave background and large-scale surveys suggest a clear number for matter density. Ordinary matter plus dark matter together make up only about 30% of the critical density. That is a large amount of mass, and it is essential for structure formation, but it is not enough to reach critical density on its own if the universe is truly flat. So the ledger looks strange. Geometry suggests the universe is very close to critical density. Matter contributes only a fraction of that. Something else must fill the gap, something that gravitates in a way that affects expansion, yet does not clump into galaxies the way matter does. At this point, it helps to emphasize the role dark matter plays, even while it remains invisible. Dark matter provides the scaffolding for the cosmic web. In the early universe, tiny density fluctuations grew under gravity. Dark matter, being effectively collisionless and not supported by pressure in the same way as ordinary gas, could begin clumping earlier and more efficiently. Ordinary matter then fell into these gravitational wells, cooling and condensing to form stars and galaxies. Without dark matter, it is difficult to produce the observed large-scale structure within the age of the universe as measured by the cosmic microwave background. So dark matter is simultaneously a solution and a problem. It solves the missing mass in galaxies and clusters and explains structure growth. But it does not solve the expansion fate question on its own, because the total matter density still appears too low to reverse expansion if the universe is flat and if no other component changes the rules. This is where the story becomes quietly tense, in a scientific way rather than a theatrical one. The universe has offered strong evidence of flat geometry. It has revealed a large quantity of unseen mass, and still, the gravitational pull from all known matter appears insufficient to account for the total energy density implied by flatness. In earlier decades, the expectation was that the universe should be slowing down, that gravity should be working as a cosmic brake. Dark matter strengthened that expectation somewhat by adding mass. But the background radiation and large-scale measurements suggested that even with dark matter included, matter is not the dominant ingredient in the cosmic budget. That is a remarkable conclusion because matter is everything that feels solid and familiar. Matter is what forms stars and planets. Matter is what forms telescopes and brains and late-night worries about the end of the universe. And yet, matter is not enough to explain the geometry of space-time itself. So the pre-acceleration worldview ends in an uneasy balance. The universe expands. Gravity should slow it. Dark matter adds hidden mass, deepening gravitational influence, and yet, the total matter content still appears to fall short of what is needed to match the universe's observed flatness without invoking something else. The measurements are not whispering at this stage. They are insisting. Either the universe is not as flat as it appears, which the data strongly argues against, or the universe contains a dominant component beyond matter, one that affects expansion in a different way. And as soon as that possibility is allowed to exist, the universe becomes ready to deliver the most surprising measurement of all, the one that will decide whether the cosmic brake is working, or whether something is pressing the accelerator instead. By the time the universe's matter budget and geometry began to look uneasy, cosmologists had a very specific plan. If gravity was slowing expansion, the slowdown should be measurable. Not by guesswork, not by philosophical preference, but by comparing how the universe expands now with how it expanded when it was younger. And the simplest way to do that is to look far away, because looking far away is also looking back in time. Light from distant galaxies set out billions of years ago, and it has been traveling ever since, stretched by expanding space, carrying with it a record of what the universe was doing when that light began its journey. To measure cosmic slowdown, astronomers needed objects bright enough to be seen across immense distances and predictable enough to serve as reliable distance markers. Type 1. A supernovae fit that role almost perfectly. They are extraordinarily luminous, sometimes briefly outshining the combined starlight of their host galaxies, and their brightness follows patterns that can be calibrated, making them useful as standard candles. That usefulness comes from the physics behind them. A Type 1. A supernova typically involves a white dwarf in a binary system. The white dwarf pulls matter from a companion star or merges with another white dwarf, pushing it toward a critical threshold known as the Chandrasekhar limit, roughly 1.4 times the mass of the Sun. At that point, the star's internal support fails, and a thermonuclear runaway disrupts the white dwarf in a catastrophic explosion. The details can vary, but the outcome is similar enough that, with careful calibration, these supernovae become dependable markers across billions of light years. In the 1990s, two major research collaborations set out to use these supernovae to measure the expansion history of the universe. One was the Supernova Cosmology Project, led by Saul Perlmutter. The other was the High Redshift Supernova Search Team, led by Brian Schmidt, with Adam Rees playing a central role. Their goal was straightforward in concept: find distant Type 1 as supernovae, measure their redshifts, measure their apparent brightness, and compare the results to what different cosmological models predict. If expansion had been slowing under gravity, then distant supernovae would appear slightly brighter than they would in a universe expanding at a constant rate. Because in the past, the universe would have been expanding faster and then gradually breaking. This was not a casual measurement. It required hunting for supernovae in faint, faraway galaxies, tracking how their brightness changed over time, correcting for dust, calibrating light curves, and controlling systematic errors. It was the kind of work where the universe does not give up its secrets to anyone in a hurry. These teams had to be patient, meticulous, and slightly stubborn, which is a wonderful combination for science and a terrible combination for casual dinner conversations. As the data accumulated, the expectation remained that expansion would show deceleration. Gravity should be pulling back. Matter, including dark matter, should be acting like a weight that slows the growth of the cosmic scale factor. Even if the universe expanded forever, it might do so while gradually easing off the accelerator, like a car coasting uphill. Then the results arrived, and they did not match that picture. The The distant Type 1a supernovae were not brighter than expected. They were dimmer. In practical terms, that means they appeared farther away than they should have been in a decelerating universe. Their light had traveled longer through expanding space than the gravity-only models predicted. The conclusion, if the measurements were correct, was simple and unsettling. Expansion had not been slowing. Expansion had been speeding up. The universe was not merely expanding, it was accelerating. This was announced in 1998, and it landed like a quiet earthquake. Not because it was shouted, but because it undermined a deeply reasonable expectation. Gravity was supposed to be the cosmic brake. Yet the data suggested the brake was not only failing, it was being outmatched by something else. The obvious first reaction was skepticism, because skepticism is part of the immune system of good science. Could dust be dimming the supernovae? Could the supernovae be evolving with cosmic time, becoming intrinsically dimmer in the distant past? Could selection effects be skewing the sample? Both teams worked hard to rule out these possibilities. The remarkable thing is that two independent collaborations using similar tools but separate analyses arrived at the same conclusion. Later surveys, improved calibrations, and additional cosmological probes reinforced the result. The universe's expansion is accelerating. In 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for the discovery of cosmic acceleration. That award did not end the story, but it marked a turning point. The acceleration result became part of the foundation of modern cosmology. Within general relativity, acceleration demands a cause. The Friedmann equations connect the expansion rate to energy density and pressure. Matter contributes energy density and essentially negligible pressure on cosmic scales. So matter produces gravitational attraction and deceleration. Radiation contributes energy density and positive pressure. And in general relativity, that positive pressure also gravitates. So radiation also contributes to deceleration when it dominates. For acceleration to occur, the universe must contain a component with a special property. It must exert strongly negative pressure. Negative pressure is one of those phrases that can sound like nonsense at first. Pressure is usually imagined as something that pushes outward, like air in a tire. But in general relativity, pressure is part of the source of gravity, and it affects how space-time evolves. The expansion's acceleration depends on the combination of energy density and pressure. One way to express the core idea in clear spoken form is cosmic acceleration depends on energy density plus 3 times pressure divided by the square of the speed of light. When that overall combination is positive, gravity behaves attractively on cosmic scales, and expansion decelerates. When that combination becomes sufficiently negative, the effect reverses, and expansion accelerates. This does not mean the universe is being pushed outward by a wind. It means the energy content of space-time has a property that makes the gravitational effect repulsive in the relevant equations. The simplest candidate for such a component was an old idea wearing a new suit, Einstein's cosmological constant. Originally, Einstein had introduced it to keep the universe static. In the late 20th century, it returned as a way to explain why the universe accelerates. If the cosmological constant represents a constant energy density inherent to empty space, then as the universe expands, that energy density does not dilute. matter spreads out and becomes less dense. Radiation spreads out and becomes less dense and less energetic. But a constant vacuum energy remains constant per unit volume. As space increases, the total amount of that energy increases because there is more space to contain it. This energy component became known as dark energy. The name is not particularly poetic, but it is accurate in the sense that it is not luminous and not directly observed. Dark energy is inferred from its gravitational influence on expansion and geometry. It is dark in the same way dark matter is dark. It does not emit, absorb, or reflect light in ways telescopes can easily use. But it is distinct from dark matter in one crucial way. Dark matter clumps. It gathers into halos around galaxies and clusters. Dark energy does not clump in that way, at least not in the simplest models. Dark energy appears to be smooth, spread throughout space-time. When cosmologists combine supernova results with cosmic microwave background measurements from missions like Planck, and with large-scale structure evidence such as baryon acoustic oscillations, the numbers point to a striking cosmic budget. Ordinary baryonic matter, the stuff of atoms, contributes only about 5%. Cold dark matter contributes roughly 25%. Dark energy contributes roughly 70%. The universe is, in a very real sense, mostly something that does not form stars and does not shine. This helps explain why earlier density accounting felt incomplete. Matter was not the full story. In a flat universe, the total energy density is close to the critical density. If matter supplies about 30% of that, something else must supply the rest. Dark energy fills the gap while also explaining why expansion accelerates. At this point, it helps to get very clear on what the cosmological constant model implies. If dark energy is truly constant vacuum energy, then its density stays the same over time. As the universe expands, matter density declines because matter spreads out. Imagine taking the same amount of paint and spreading it across a larger and larger canvas. The paint layer becomes thinner. That is matter density. Vacuum energy does not thin in that way in the cosmological constant model. Its density remains constant as the canvas expands. Over time, that means dark energy becomes more and more dominant, because matter becomes increasingly diluted, while dark energy does not. This leads to a key moment in cosmic history. Early on, the universe was dominated by radiation. Later, it became dominated by matter. In the more recent universe, dark energy becomes dominant. When dark energy takes over, the expansion changes character. Instead of slowing under gravity, expansion begins to accelerate. Observations suggest that this transition happened several billion years ago. The universe did not accelerate strongly in the early era. It spent a long time in a matter-dominated phase where structure could form, where gravity could pull matter into galaxies and clusters, where stars could ignite and build heavy elements. Then, as matter density diluted, dark energy gradually rose to dominance. Once it dominated, acceleration became the defining feature of the cosmic expansion. To describe dark energy more generally, cosmologists use an idea called the equation of state, which relates pressure to energy density. In spoken English, one can say pressure equals a constant factor multiplied by energy density. If that constant factor equals -1, dark energy behaves exactly like a cosmological constant. Measurements of distant supernova, combined with cosmic microwave background data and galaxy surveys, indicate that the factor is very close to -1 within current uncertainties. That is one reason the cosmological constant remains the simplest and most widely accepted interpretation. But the phrase, "within current uncertainties," is not a footnote. It is the opening of a door. If the equation of state differs slightly from the cosmological constant value, then dark energy might not be constant. It might evolve with time. And if it evolves, the far future of the universe could change. One possible alternative to the cosmological constant is a dynamic field, often called quintessence. In these models, dark energy is not a constant property of empty space, but a field that changes slowly as the universe expands. Its energy density could decrease or increase over time. Its pressure could shift. Such models can be tuned to mimic a cosmological constant closely enough to match current observations, but they introduce additional complexity and require careful testing. Another broad possibility is that the acceleration is not caused by a new energy component at all, but by a modification to general relativity on extremely large scales. In this view, gravity itself might behave differently across cosmological distances or at very low densities. Many such theories have been proposed. The challenge is that general relativity is extraordinarily well tested in the solar system, around stars in gravitational lensing and through gravitational waves observed by collaborations like LIGO and Virgo. Any modification must reproduce those successes while also explaining cosmic acceleration. So far, no alternative has clearly outperformed the standard model across the full range of observations. Even within the cosmological constant interpretation, a deeper problem remains. Quantum field theory suggests that empty space should contain vacuum energy due to fluctuations of quantum fields. In principle, every quantum field contributes some amount of energy to the vacuum. The puzzle is that naive calculations of vacuum energy density yield a value that is absurdly larger than what is observed. The discrepancy is so large that it is often described in terms of many orders of magnitude, a mismatch that makes physicists uncomfortable in a way that is almost philosophical. The observed dark energy density is tiny in particle physics terms, yet cosmologically dominant in its effects. This is sometimes called the cosmological constant problem. It does not threaten the observation that acceleration exists. It threatens the comfort of explaining it using simple quantum intuition. Dark energy is measured. Its physical origin remains uncertain. Despite that uncertainty, the observational implications are clear. If dark energy behaves like a cosmological constant, expansion will not slow towards zero. It will continue to accelerate, not necessarily in a dramatic way that looks like something is speeding off, like a rocket, but in the mathematical sense that the rate of expansion increases with time rather than decreases. That has consequences for what can be observed. In an accelerating universe, there exists a cosmic event horizon, a boundary beyond which events can never affect an observer because space expands too quickly for light to cross the growing distance. Over time, more and more galaxies will slip beyond this horizon. Their light will be stretched into longer wavelengths, becoming dimmer and harder to detect, eventually disappearing from view entirely. In the far future, observers within a gravitationally bound region such as the local group would see a universe that appears emptier, with fewer visible galaxies, not because the galaxies vanished, but because the expanding space placed them beyond reach. This does not mean local structures dissolve. In the cosmological constant model, the expansion is gentle enough that galaxies, solar systems, and atoms remain bound. What changes is the connectivity of the cosmos. The large-scale universe becomes increasingly fragmented into isolated islands of gravitational binding. And this brings the original question into a sharper, more modern form. The question is not simply whether gravity will eventually stop expansion. Under the current measurements, gravity from matter is not strong enough to do that. The question becomes whether dark energy remains constant, weakens, strengthens, or transforms. If it remains constant, expansion continues indefinitely, accelerating toward a future of isolation and cooling. If it weakens, gravity could become more influential again. If it strengthens, acceleration could become more extreme. Each of those possibilities corresponds to a different long-term fate, and the best evidence so far points toward the simplest case. Dark energy behaving like a cosmological constant. There is a strange calmness in that conclusion. The universe does not appear to be preparing for collapse. It does not appear to be slowing. It appears to be carried outward by something smooth and persistent, an energy associated with space itself. And while the physical explanation is still incomplete, the measurements are consistent across multiple methods. The universe expands. The expansion accelerates. And the cosmos, which once seemed like a fixed backdrop, turns out to be a living geometry, evolving according to rules that can be written down, measured, and tested, even if the deepest origin of the most important component remains. For now, one of nature's quietest secrets. Once dark energy enters the story, the universe stops being a simple tug-of-war between outward expansion and inward gravity. It becomes something closer to a three-way balance between geometry, energy density, and pressure. And geometry in cosmology is not a decorative word. It is one of the main levers that decides what kind of universe exists and what kind of future it can have. On the larger scales, the universe can be described as having one of three broad spatial curvatures. Space can be positively curved, meaning it resembles the three-dimensional analog of a sphere. Space can be negatively curved, meaning it resembles the three-dimensional analog of a saddle. Or space can be flat, meaning that, averaged across enormous distances, it behaves like Euclidean space. In flat space, the angles of a triangle add to 180 degrees, and parallel lines remain parallel. These are simple images, but the deeper meaning is physical. Curvature affects how light travels and how volumes grow with distance. It also reflects the total energy density of the universe. In the Friedmann framework, the critical density is the dividing line that connects energy density to geometry. If the total energy density is greater than the critical density, the universe is closed and positively curved. If the total energy density is less than the critical density, the universe is open and negatively curved. If the total energy density equals the critical density, the universe is flat. That connection is one of the most elegant results in modern cosmology, because it turns a seemingly abstract geometric question into something measurable through observations of the real sky. One of the strongest measurements of large-scale curvature comes from the cosmic microwave background radiation, mapped in detail by the Planck satellite. The early universe contained pressure waves in its hot plasma, a kind of cosmic sound. Those waves left behind a characteristic scale, a preferred size imprinted in the temperature fluctuation pattern. When that physical scale is projected onto the sky, its apparent angular size depends on the geometry of space between then and now. In a positively curved universe, light paths converge and the feature appears larger. In a negatively curved universe, light paths diverge and the feature appears smaller. Planck's measurements indicate that the universe is very close to spatially flat, within a small margin of error. Flatness is sometimes described as if it were a philosophical aesthetic choice, like the universe deciding to be neat and tidy. In reality, flatness is a numerical statement. It means that the total energy density of the universe is extremely close to the critical density. That result fits beautifully with the broader picture in which cosmic inflation, proposed by Alan Guth in the early 1980s and developed by many others, drove the universe toward flatness through a brief period of extremely rapid early expansion. Inflation is not the focus here, but it is worth noting because it provides a natural explanation for why flatness is not an improbable accident. Now comes the subtle point that can feel surprising. Flatness does not automatically mean the universe slows towards stillness. In a universe that contains only matter and radiation, a flat geometry would imply that expansion continues forever while gradually slowing, approaching zero only in the limit of infinite time. But when dark energy dominates, geometry and destiny shift. A flat universe with a cosmological constant does not coast to a halt, it accelerates. So the most important question becomes not only what the curvature is, but what the energy content is. Matter density dilutes as space expands. Radiation density dilutes even faster because radiation loses energy through redshift. Dark energy, if it behaves like a cosmological constant, does not dilute at all. Its density remains constant per unit volume. Over time, that means dark energy becomes ever more dominant compared to matter and radiation. And once dark energy dominates, the expansion rate does not decline. It approaches a kind of steady acceleration. This leads to the future scenario that is most consistent with present measurements, often called the Big Freeze, also known as heat death. These names can sound dramatic, but the reality is not a sudden catastrophe. It is a slow drift toward a colder, darker, more dilute universe. The underlying physical idea is thermodynamic. The second law of thermodynamics states that in an isolated system, entropy tends to increase. Entropy is often described as disorder, but it is more precise to think of it as the dispersal of energy into forms that are less useful for doing work. Stars shine because there are large energy gradients, hot interiors and cooler surroundings. Life and complexity, where they exist, also rely on gradients. A universe that becomes smoother, colder, and more uniform loses the ability to support energy flows that create new structure. At present, the universe is rich in structure. Galaxies cluster, filaments stretch across space, stars form, and heavy elements cycle through generations of stellar birth and death. But even now, there are hints that the universe is moving past its most active era. Observations of galaxy populations across cosmic time show that star formation peaked roughly 10 billion years ago and has been declining since. Many galaxies, including large elliptical galaxies, are already dominated by old stars and show little new star formation. Spiral galaxies like the Milky Way still form stars, but even here the fuel supply is not infinite. In the far future of a dark, energy-dominated universe, the decline in star formation becomes a defining feature. Cold gas in galaxies is gradually consumed by star formation or heated and expelled by stellar winds and supernova feedback. Gas can also be locked away in compact objects. Over very long timescales, the raw material for making new stars becomes scarce. Massive stars burn their fuel quickly and die young. They end as core collapse supernovae, leaving neutron stars or black holes. Sun-like stars evolve more slowly, ending as white dwarfs after shedding their outer layers in planetary nebulae. Red dwarf stars, the most common stars in the universe, burn their hydrogen extremely slowly and can shine for trillions of years. If the universe continues expanding for trillions of years, red dwarfs will be the last long-lived lamps in an otherwise quiet cosmos. Eventually, even they exhaust their usable fuel and fade. As the universe ages, galaxies become populated mostly by stellar remnants. White dwarfs cool steadily, radiating away their remaining heat. Neutron stars lose rotational energy and magnetic activity over time. Black holes continue to exist as deep gravitational wells. The universe becomes, in a very literal sense, less luminous. At the same time, acceleration changes what can be seen. In an accelerating universe, there exists a cosmic event horizon. This horizon is not a physical wall in space. It is a boundary defined by the expansion history. Light emitted beyond a certain distance can never reach an observer because the space between them grows too quickly. Over time, more galaxies cross this horizon. Their light becomes increasingly redshifted, stretched to longer wavelengths, and dimmed. Eventually, they disappear from view. In the distant future, observers inside a gravitationally bound region, such as the local group, would see a dramatically emptier sky. The local group includes the Milky Way, Andromeda, and many smaller galaxies, and it is bound strongly enough that it does not participate in the expansion in the same way distant galaxies do. The Milky Way and Andromeda are expected to merge in a few billion years, forming a single large galaxy. That merged galaxy would remain bound, but everything beyond the local gravitational neighborhood would gradually fade away across the horizon. This is one of the strangest features of the Big Freeze scenario. The universe does not end in an explosion. It ends, in a sense, in loneliness. Not emotional loneliness, but physical isolation. The large-scale structure becomes inaccessible. The cosmic web stretches beyond reach. The observable universe becomes smaller in content, not because space shrinks, but because more of space becomes causally disconnected. This process is slow enough that it can be described without drama. The universe becomes more dilute. Energy becomes more spread out. Fewer new stars form. Existing stars burn out. Distant galaxies slip beyond view. The temperature of the universe continues to decline as expansion stretches radiation to longer and longer wavelengths. To appreciate the timescales, it helps to anchor the present. The universe is about 13.8 billion years old. That is a long time by human standards, but it is a small fraction of the timescales involved in the far future. Red dwarf stars can shine for trillions of years. That is hundreds of times the current age of the universe. White dwarfs can cool for far longer. Black holes, if Hawking radiation is correct, persist for timescales so enormous that normal language begins to feel inadequate. Stephen Hawking predicted that black holes emit radiation due to quantum effects near the event horizon. This process, called Hawking radiation, causes black holes to lose mass extremely slowly. A black hole with the mass of the Sun would take a timescale on the order of 10 to the power of 67 years to evaporate completely, which is a 1 followed by about 67 zeros. A supermassive black hole with millions of solar masses would take even longer, on the order of 10 to the power of 100 years, which is a 1 followed by about 100 zeros. These numbers are so far beyond the age of the universe that they describe a kind of time that barely feels like time at all. If the universe continues expanding under a cosmological constant, then after unimaginably long epochs, black holes evaporate, and the remaining universe becomes an extremely thin soup of low-energy photons and a small number of particles. Energy is spread out almost uniformly. Entropy is high. There are no strong gradients left to power complex processes. This is heat death, the big freeze, a universe that still exists but has become quiet, cold, and diffuse. This is the most widely supported future because it follows directly from the simplest interpretation of dark energy as a cosmological constant, combined with the observed flatness of the universe and the measured matter density. But it is not the only possible future, and it is important to explain why, without implying uncertainty where there is strong consensus. The consensus is that expansion is accelerating. The consensus is that the equation of state for dark energy is consistent with a cosmological constant, meaning pressure is close to negative energy density in magnitude. The consensus is that the universe is close to flat. The uncertainty lies in whether dark energy is exactly constant forever, or whether it evolves slowly over cosmic time in a way that current measurements cannot yet detect. If dark energy is not constant, then the future could deviate from the big freeze scenario. If dark energy weakens over time, acceleration could slow. In extreme cases, expansion could even return to a decelerating regime dominated by matter, though the measured matter density still makes reversal difficult without additional changes. If dark energy strengthens over time, acceleration could become more intense, leading toward more extreme outcomes. But these are possibilities, not current best evidence. It also helps to keep geometry in view. Flatness does not guarantee a big freeze, but it makes a big crunch difficult under current energy measurements. If the universe is flat and dark energy remains positive and constant, there is no mechanism in the standard model for expansion to stop. A closed, positively curved universe could in principle recollapse if dark energy were absent or reversed, but the data do not indicate that we live in such a universe. The measurements point toward flat geometry and a dominant dark energy component. So geometry and energy content reinforce the same conclusion. The universe is not set up for a graceful slowing into stillness. It is set up for continued expansion, continued acceleration, and a slow drift toward a colder state. It is worth noticing how this changes the emotional texture of the original question. Will the universe stop expanding sounds like a question about a finish line, as though the universe might one day run out of momentum and settle down. The modern picture is different. Expansion is not a leftover shove from the beginning. Expansion is an evolving behavior tied to what the universe contains. And because dark energy does not dilute the way matter does, the universe becomes more dominated by the component that drives acceleration as time goes on. So the most likely future is not a universe that slows and rests. It is a universe that keeps stretching, gradually thinning out everything that is not gravitationally bound, gradually dimming the sky, gradually leaving islands of matter more isolated from one another, until even those islands fade into a sea of low-energy radiation. That may sound bleak if imagined too quickly, but it can also be understood as a simple, steady consequence of known physics. No sudden ending is required. The universe does not need an apocalypse to change profoundly. Sometimes all it needs is time. Lots of time and a gentle acceleration that never quite stops doing what it does. The Big Freeze picture has a kind of steady logic to it. Dark energy stays constant, matter thins out, distant galaxies fade beyond the cosmic event horizon, and the universe slides toward a colder, emptier state. But cosmology has learned to be careful about the word constant, because it often hides an assumption that may be true, or may only be approximately true within current measurement limits. If dark energy is not exactly a cosmological constant, then the future can change in ways that are not just different in detail, but different in kind. One of the most extreme alternatives begins with a single shift in the behavior of dark energy. In the cosmological constant picture, dark energy has a pressure that is negative and roughly equal in magnitude to its energy density. In spoken terms, it behaves as though the pressure is pushing outward while remaining smooth and uniform across space. But there are models in which the negative pressure is even stronger than the cosmological constant case. When that happens, dark energy does not merely dominate. It grows more powerful as the universe evolves. This class of models is often described using the term phantom energy. The word phantom is less important than the property it points to. In these models, the effective equation of state leads to an energy density that increases with time as the universe expands, rather than staying constant. That is a dramatic departure from the Big Freeze scenario. It means that as space grows, dark energy becomes denser, not thinner. The repulsive gravitational effect strengthens, not stabilizes. If that were true, the future would not be a slow dimming alone. The future could include a final, finite time event in which the expansion becomes so intense that it begins to overcome forces that normally hold structures together. This scenario is called the Big Rip. The logic of the Big Rip is disturbing in its simplicity. Structures in the universe remain intact because the forces binding them are stronger than the expansion across their scale. Galaxy clusters are bound by gravity. Galaxies are bound by gravity and by the stable orbits of their stars in dark matter halos. Solar systems are bound by the gravity of their stars. Planets are held together by electromagnetic forces between atoms. Atoms themselves are held together by electromagnetism between electrons and nuclei are held together by the strong nuclear force. In the standard Big Freeze picture, expansion never becomes strong enough to challenge those bindings on small scales. It only separates large-scale structures from one another. But if phantom energy grows in density, the acceleration becomes stronger and stronger. The expansion rate does not just continue, it increases more rapidly over time. At first, the Big Rip would look like an exaggeration of the universe's current trend. Distant galaxies would recede faster. The cosmic event horizon would become more restrictive. The observable universe would empty out more quickly as regions slip beyond causal contact. Still, local structures would remain intact for a long time. Gravity inside galaxy clusters and galaxies would continue to hold their members together. Then, at some point, the repulsive effect would begin to compete with gravitational binding at the largest bound scales. Galaxy clusters would be the first to lose coherence. The space between galaxies inside clusters would stretch quickly enough that the cluster's gravity could no longer keep its galaxies bound. The cluster would dissolve into separated galaxies. As phantom energy continued to strengthen, the next step would be the disruption of galaxies themselves, Stars orbit the centers of galaxies because the combined gravity of stars, gas, and especially dark matter halos provides a deep gravitational well. In a Big Rip scenario, expansion could become strong enough that this binding is overcome. The galaxy would no longer function as a stable system. Stars would drift away from the galactic center, no longer held in orbit. After that, smaller bound systems would be threatened. Solar systems would become unbound. Planets would no longer remain in stable orbits around their stars. The gravity of a star that has held planets for billions of years would be outmatched by the accelerating expansion at that scale. Planets would drift away, not because they are pushed by a wind, but because the geometry of space-time would be changing too aggressively for gravity to maintain coherence. In the most extreme version of this scenario, the process continues inward. Planets would be torn apart if the expansion became effective on planetary scales. Then, molecules could be disrupted, because the electromagnetic bonds that hold atoms together in chemical structures would no longer keep up with the stretching of space. Then atoms themselves could be pulled apart, meaning electrons could no longer remain bound to nuclei. In the final stage, even nuclei might be disrupted if the expansion becomes effective at nuclear scales. At that point, the concept of stable matter becomes meaningless. The universe would not just be empty, it would be shredded. The striking feature of the Big Rip is that it happens in a finite time. The expansion rate diverges to infinity at a particular future moment. This is not an endless fading like the Big Freeze. It is a deadline built into the mathematics of a universe in which dark energy density increases over time in the phantom energy way. Now comes the crucial point for scientific honesty. There is no strong evidence that this is our universe's future. Observations constrain the behavior of dark energy through multiple probes. Distant Type 1 are supernovae, baryon acoustic oscillations and galaxy surveys, and the cosmic microwave background. These measurements indicate that dark energy behaves very closely to a cosmological constant, meaning the simplest interpretation remains a constant energy density with steady negative pressure. The phantom energy case is not favored by the bulk of the data. It remains at most a possibility within uncertainties and within certain theoretical constructions, not a prediction. So the Big Rip is valuable as a contrast. It shows how sensitive cosmic destiny is to the exact properties of dark energy. A small change in the way dark energy behaves over time can turn the far future from a slow dimming into a finite time disintegration. The Big Freeze and the Big Rip sit on one side of the cosmic fate discussion because both assume expansion continues. The difference is whether expansion accelerates gently and steadily, or whether it accelerates in a runaway way. On the other side sits the older, once more popular expectation, the possibility that expansion might stop and reverse, leading to contraction. This is the Big Crunch. The Big Crunch scenario is the natural counterpart to the Big Bang in a certain sense. If the universe is expanding now, and if gravity is strong enough, and no repulsive component dominates, then expansion could slow, halt, and reverse. The scale factor would begin decreasing. Galaxies would approach one another. The universe would become denser and hotter. In the final stage, it could collapse into a very dense state. This scenario emerges naturally in a universe that is closed and positively curved, meaning its total energy density exceeds the critical density, and where dark energy is absent or behaves in a way that does not prevent collapse. In a simple matter-dominated universe, if the density parameter is greater than 1, gravitational attraction eventually wins. Expansion stops. Contraction begins. The universe ends in a crunch rather than a freeze. But the modern universe does not seem to be built that way. Measurements from the Planck satellite indicate spatial flatness to high precision. The total energy density is extremely close to the critical density. Matter density, including dark matter, is only a fraction of that total. Dark energy accounts for the remainder, and the expansion is accelerating, not decelerating. Under those measured conditions, a big crunch is not the natural outcome. To bring it back into plausibility, something must change. There are a few broad ways that could happen. The first is that dark energy is not constant and might weaken over time. If dark energy density decreases, then matter could eventually regain dominance, because matter dilutes with expansion, but might still be the main gravitating component if dark energy fades away. In that case, the expansion could return to a decelerating regime. A decelerating regime does not guarantee a big crunch, but it opens the door to one if the total density and curvature are aligned appropriately. The second way is more dramatic. Dark energy could change sign, meaning the effective pressure and energy density could evolve into something that behaves like an attractive component rather than a repulsive one. In practical terms, that would mean the component currently accelerating expansion would begin to contribute to deceleration instead. If such a transition occurred, it could drive the universe toward recollapse, even if it is currently expanding. Some speculative scalar field models allow such behavior, though they are constrained by observations and require careful tuning. A third way involves modifications to general relativity on cosmological scales. If gravity behaves differently across enormous distances, it might permit a future in which acceleration is temporary. The standard model assumes general relativity is correct on these scales, and current observations strongly support it, but cosmology remains open to the possibility that new gravitational physics might emerge at extremely low densities or over enormous times. At the moment, none of these changes is supported by direct evidence. The simplest interpretation of the data remains that dark energy behaves like a cosmological constant and that acceleration persists. This makes the Big Crunch unlikely under known conditions. It also clarifies the deeper reason why. In the Friedmann equations, the expansion's fate depends not only on density, but on pressure. Matter is attractive. Radiation is attractive. A cosmological constant acts repulsively. As the universe expands, matter becomes less dense. If dark energy stays constant, it becomes ever more dominant. That dominance makes it difficult to imagine gravity staging a comeback without a fundamental change in the properties of dark energy itself. This is why cosmologists often describe the Big Crunch as a scenario that would require new physics or a significant shift in our understanding of dark energy. It is not ruled out by logic, It is ruled out by the best current measurements unless those measurements are incomplete in a specific way. There is also a subtle point about observational time that matters here. The universe has been accelerating for several billion years, but that is still a small portion of the cosmos's total lifespan if it expands forever. It is possible, in principle, that dark energy behaves one way for a while and another way later. Observationally, humans can only measure the universe during the era they exist in. Cosmology can infer the past from the relic signals still visible now. It cannot observe the far future directly. That is why careful language matters. The best evidence indicates dark energy behaves like a cosmological constant now, and over the observable past. That evidence supports continued acceleration, but it does not constitute a direct observation of eternity. This is where scientific restraint becomes important. Some outcomes are strongly disfavored by current data, but they are not metaphysically impossible. The Big Rip requires dark energy to be more extreme than current measurements suggest. The Big Crunch requires dark energy to weaken or reverse in a way not supported by current measurements. The Big Freeze requires dark energy to remain close to a cosmological constant, which is the scenario most consistent with present evidence. In other words, the universe has presented a small menu of endings, and the data currently points most strongly toward the one that looks least like an ending at all. The way to hold these futures in mind is not as competing dramas, but as physical consequences of measurable parameters. The far future depends on the equation of state of dark energy, the total energy density relative to critical density, and the large-scale curvature of space-time. Those are empirical questions. They can be measured more precisely over time as surveys improve. They can be constrained by new observations of supernovae, galaxy clustering, weak gravitational lensing, and the cosmic microwave background. For now, the evidence suggests a universe that expands forever. It does not suggest a universe that will reverse and collapse. It does not strongly suggest a universe that will rip itself apart. It suggests a universe that keeps stretching, quietly, persistently, with acceleration that is real but not yet understood at the deepest physical level. And that takes the original question and turns it into a more precise one. The question is not only whether the universe will stop expanding. The question is whether the physics currently driving acceleration remains stable over the long run, or whether it is the surface expression of a deeper mechanism that changes with time. The universe's future is not written only in how much matter it contains. It is written in how space-time responds to the most mysterious component in the cosmic budget. That mystery does not mean anything goes. The cosmos is still constrained by the measurements already made. It simply means that, even with an accelerating universe, the final answer has a hinge, and that hinge is the true nature of dark energy. Once the mind accepts that dark energy might be the long-term driver of expansion, another question appears, almost like a shadow behind the first. If the universe is allowed to expand forever, does it have to be a one-way journey? Or could it be part of something larger, something repeating? Something that resets the clock without needing an outside hand to wind it up again. This is where cosmology becomes both bold and disciplined. Bold because it reaches for ideas that stretch far beyond direct observation. disciplined because the universe still has to obey what is already measured, including the cosmic microwave background mapped by Planck, the accelerating expansion revealed by Type 1a supernova surveys, and the large-scale structure traced by galaxy surveys. Any alternative must respect those constraints while offering a coherent physical mechanism. One family of alternatives is built around the idea of cycles. In cyclic cosmologies, the universe does not begin once and then expand forever. Instead, it expands, changes state, and in some way becomes the seed of a future beginning. This does not necessarily mean a literal bounce where everything collapses into a point and explodes again. Some cyclic proposals avoid a conventional crunch entirely. They attempt to connect the remote future of an expanding universe to a new beginning through deeper mathematical or physical symmetries. A striking example is conformal cyclic cosmology, proposed by Roger Penrose. Penrose is one of the central figures in modern gravitational physics, known for foundational work on black holes, singularities, and the mathematical structure of space-time. In conformal cyclic cosmology, the universe is divided into aeons. Each aeon begins in a hot, dense state and ends in a cold, extremely expanded future. The key move is to notice that, in the far future, if massive particles effectively disappear, the universe becomes dominated by radiation and other forms of energy that do not have a fixed mass scale in the same way. When only massless or effectively massless entities remain, space-time can be described in a way that is insensitive to overall scale. Penrose uses this idea to argue that the infinitely expanded future of one aeon can be conformally rescaled to resemble the hot, dense beginning of the next aeon. In this picture, the universe does not need to contract to restart. It needs to age so thoroughly that the concept of a fixed length scale fades away. A new beginning emerges not from collapse, but from a transformation of what scale means in the physics. It is an elegant idea, and it carries a certain quiet audacity, because it suggests that the end of one universe can look, in the right mathematical light, like the start of another. Conformal cyclic cosmology is not universally accepted. Some claims about potential observational signatures, such as special patterns in the cosmic microwave background, have been debated. The Planck collaboration's data has been mined extensively for anomalies, and while the universe does contain curiosities and statistical oddities, the standard inflationary picture remains the best supported explanation for the overall structure of the background. Conformal cyclic cosmology remains an active, provocative proposal rather than a settled alternative. Still, it illustrates a crucial point. Even an eternally expanding universe might, in principle, connect to something like a new beginning without requiring a conventional recollapse. A different kind of reset appears in bounce models, where contraction does occur, but the universe avoids a true singularity through quantum gravitational effects. Classical general relativity, when traced back to the earliest times, leads to a singularity in the simplest Big Bang models, a point where density and curvature diverge and the theory stops making physical predictions. Many physicists interpret that singularity not as a real object in nature, but as a sign that general relativity is incomplete without quantum mechanics. Loop quantum gravity is one approach to quantum gravity, aiming to quantize space-time itself rather than treating it as a smooth background. In loop quantum gravity, geometric quantities like area and volume take discrete values, as though space-time has a kind of atomic structure. Loop quantum cosmology applies ideas from loop quantum gravity to the universe as a whole. In some versions, the Big Bang singularity is replaced by a quantum bounce. The universe contracts to a high but finite density. Quantum gravitational effects become repulsive, and the universe transitions into expansion again. Researchers such as Abhay Ashtekar have been prominent in developing loop quantum cosmology and exploring its consequences. These models can reproduce many features of the standard cosmological picture while replacing the initial singularity with a prior contracting phase. The bounce is not a poetic flourish. It is a mathematical consequence of how quantum geometry behaves at extreme densities, at least within the approximations used. As with other alternatives, the challenge is observational connection. The cosmic microwave background contains information about the early universe, but it is filtered through inflationary dynamics and subsequent evolution. Some bounce models attempt to produce distinctive signatures, such as subtle differences in the power spectrum of primordial fluctuations. So far, no unambiguous signature has displaced the standard inflationary interpretation. But bounce cosmology remains a serious candidate for addressing the singularity problem, and it offers a natural way to imagine a universe that existed before the Big Bang, without requiring an outside creator or a literal beginning of time. Another family of cyclic ideas comes from brane cosmology and the ekpyrotic scenario, associated with Paul Steinhardt and Neil Turok. In these models, the universe we observe is linked to higher dimensional physics, where our visible cosmos may be a kind of brane embedded in a larger dimensional space. A cycle can occur through collisions or interactions between branes, producing a hot, dense state that resembles a Big Bang from our perspective. The ekpyrotic phase is often described as a slow contraction with a stiff equation of state that smooths and flattens the universe, providing an alternative route to some of the things inflation explains. These models are imaginative, but they are also tightly constrained by data. Inflation, proposed by Alan Guth and developed by many others, remains remarkably successful at explaining the observed flatness, the near uniformity of the cosmic microwave background, and the spectrum of primordial fluctuations. Alternatives must reproduce these successes without introducing conflicts. That is not impossible, but it is difficult. In cosmology, elegance is not enough. The universe must match its own receipts. Even if none of these cyclic or bounce ideas ultimately replaces the standard picture, they are valuable because they reframe the original question. If expansion continues indefinitely, the far future might not be an absolute end. It might be a boundary where known physics changes form. Or it might be an era where scale itself loses meaning. Or it might simply be the far future, full stop. The honest position is that the data strongly supports acceleration and a dark energy component consistent with a cosmological constant, while the deeper theoretical interpretation remains unsettled. And that unsettled interpretation leads to one of the most famous discomforts in modern physics: the vacuum energy problem, often discussed as the cosmological constant problem. In quantum field theory, what humans call empty space is not truly empty. Quantum fields exist everywhere, and even in their lowest energy states, they can exhibit fluctuations. These fluctuations are not little particles popping in and out of existence like cartoon bubbles, but they do imply that the vacuum has a baseline energy. In ordinary contexts, vacuum energy can have measurable effects. One example is the Casimir effect, predicted by Hendrik Casimir, in which quantum vacuum fluctuations produce an attractive force between closely spaced conducting plates. This is a small-scale laboratory phenomenon, but it illustrates that vacuum properties are not mere philosophical abstractions. If vacuum energy exists, then in general relativity it should gravitate. A uniform vacuum energy density would behave like a cosmological constant, contributing to the expansion dynamics of the universe. That sounds promising, almost too perfect. Dark energy could simply be vacuum energy. The problem is the size of it. When physicists estimate the vacuum energy density by summing contributions from quantum fields, the naive result is staggeringly larger than the dark energy density inferred from cosmological observations. The mismatch is not a factor of 2 or 10. It is a mismatch by an absurd number of orders of magnitude. It is the kind of discrepancy that makes physicists stop smiling when they talk, because it suggests a deep misunderstanding somewhere in the conceptual plumbing between quantum theory and gravity. There are a few ways people respond to this problem, and none of them are fully satisfying. One response is that the naive calculation is not physically meaningful because quantum field theory includes procedures like renormalization. In many quantum calculations, raw infinities or huge terms appear, and the theory is handled in a way that yields finite, accurate predictions for observable quantities. Perhaps vacuum energy is similar. Perhaps what matters is not the absolute value of vacuum energy, but differences in energy. That is often true in non-gravitational physics, where energy can be shifted by a constant without changing outcomes. In gravity, absolute energy matters because it curves space-time. That makes the vacuum energy problem harder to sweep away. Another response is that different contributions cancel. Perhaps multiple fields contribute vacuum energy with opposite signs, and the net result is small. Supersymmetry, a theoretical symmetry relating bosons and fermions, would produce cancellations between contributions. But supersymmetry has not been observed at accessible energies in experiments like those at the European Organization for Nuclear Research, commonly known as CERN, using the Large Hadron Collider. Even if supersymmetry exists at higher energies, it would need to be broken in a way that still leaves the observed tiny vacuum energy density. This is possible in principle, but it is not clean. Another response is that dark energy is not vacuum energy at all. It could be a dynamic field, such as quintessence, evolving slowly over cosmic time. That can be arranged to produce an effective negative pressure. But dynamic fields bring their own questions. Why does the field's energy density have the value it has now? Why is it becoming dominant in the present cosmic era? This is sometimes called the coincidence problem, because it seems surprising that dark energy becomes dominant at a time when observers exist to notice it. Again, this might be an accident of perspective, or it might hint at a deeper mechanism. A further response involves the idea of a multiverse and anthropic selection, often discussed in the context of string theory. String theory, associated with many researchers, including Edward Witten and Leonard Susskind, suggests that the fundamental description of nature may involve extra dimensions and a landscape of possible vacuum states. In some interpretations, different regions of a larger multiverse could realize different vacuum energies. If the cosmological constant were much larger than observed, the universe might expand so rapidly that galaxies never form. Without galaxies, stars and planets would not form in the same way, and observers like humans would not exist to measure anything. In this view, the observed small value is not derived from first principles, but selected because it allows complex structure. This anthropic reasoning is controversial. Some physicists consider it a pragmatic explanation, given a landscape of possibilities. Others consider it a retreat from the goal of finding a unique, predictive theory. What is clear is that the vacuum energy problem presses directly on the boundary between what is measured and what is understood. The core discomfort remains. The simplest explanation for dark energy is a cosmological constant, and the simplest physical source for a cosmological constant is vacuum energy. But the naive quantum prediction for vacuum energy is wildly different from the observed value. Something is missing. That missing piece could be a new symmetry, a new cancellation mechanism, a new understanding of gravity, or a new way to interpret quantum vacuum contributions. It could also be that the observed dark energy is not truly constant and that future measurements will reveal subtle evolution. Observatories such as the Vera C. Rubin Observatory and the European Space Agency's Euclid mission are designed to measure cosmic expansion and structure growth with greater precision, tightening constraints on the equation of state of dark energy through weak gravitational lensing and galaxy clustering patterns. There is an important balance to maintain here. The observational claim that expansion is accelerating is strong. It is supported by independent probes. The claim that dark energy is consistent with a cosmological constant is also well supported within current errors. The uncertainty is not whether acceleration exists. The uncertainty is why the most dominant component in the universe has the value it has, and whether it is truly constant forever. This is where the original question, will the universe ever stop expanding, becomes almost two questions layered on top of each other. The first is empirical. Given present measurements, does the universe appear to be heading toward a halt? The best evidence says no. Under the standard lambda cold dark matter model, expansion continues indefinitely and acceleration persists. The second is foundational. Do current theories actually explain the thing that drives acceleration? The honest answer is not fully. Physics can describe dark energy's effects with precision, but it does not yet provide a satisfying derivation of its origin. The vacuum energy problem remains unresolved. Quantum gravity remains incomplete. The bridge between the larger scales and the smaller scales still has missing planks. And yet, this is not a story of ignorance. It is a story of a boundary being defined. The universe has told physics what the answer must look like, at least in its broad outlines. There is a small, smooth, persistent component of energy that affects the expansion of space-time on the largest scales. It behaves very close to a cosmological constant. It dominates the cosmic budget today. It appears to shape the long-term future. Whether it is truly the vacuum energy of quantum fields, whether it is a dynamic field, whether it reflects a deeper law of gravity, or whether it is an emergent effect of space-time itself, is still open. But the measurements are not waiting for theory to catch up. The universe expands. The expansion accelerates. And the most likely future, given what is currently known, is a continuing stretching that does not end in a natural halt. If that future is part of a larger cycle, then the cycle is subtle, not an obvious bounce seen in the sky like a heartbeat. It would be hidden in deep time. in the extreme far future, or in physics that only reveals itself near densities and energies beyond current reach. The universe may still have surprises left. It always has. But those surprises, if they come, will still have to fit inside the frame drawn by the evidence already written across the sky. There is a quiet boundary built into every cosmic measurement, and it has nothing to do with the power of telescopes or the cleverness of people using them. It is simply the fact that light takes time to travel. When looking at distant galaxies, the eye is not seeing them as they are right now. The eye is seeing them as they were when their light began its long journey. That is not a poetic idea. It is a hard limit. It means the universe offers only a time-delayed version of itself, stitched together from messages that have been traveling through expanding space for billions of years. This is why the phrase, "the observable universe," matters so much. It does not mean the whole universe. It means the part of the universe that can, in principle, be observed because light has had time to reach an observer since the early, hot, dense phase. The observable universe is defined by a horizon, often called the particle horizon. It marks the greatest distance from which light could have traveled to reach an observer since the universe became transparent, and in practice since the beginning of the expansion described by the Big Bang model. Because the universe has been expanding while light traveled, the particle horizon distance is not simply the age of the universe multiplied by the speed of light. Expansion stretches the path, so the observable radius ends up being much larger than the universe's age in light years. This can sound like a contradiction until it is held gently. The universe is about 13.8 billion years old, but the observable radius is roughly 46 billion light years. That does not mean anything traveled faster than light through local space. It means the space through which that light traveled expanded while the light was on the way. So the present-day distance to those sources is larger than the distance light crossed at the time. The past was closer. The present is farther. The particle horizon is about what can be seen from the past. But in an accelerating universe, another horizon becomes just as important, and it points in the other direction. This is the cosmic event horizon. It is not the furthest distance from which light has reached an observer. It is the furthest distance from which light emitted now can ever reach an observer, even if time continues forever. This idea can feel almost unfair, as if the universe is imposing a permanent information embargo. In a decelerating universe, the event horizon can be absent. Given enough time, light from very distant regions can eventually arrive. In an accelerating universe dominated by a cosmological constant, the event horizon exists because space expands so persistently that beyond a certain distance, the gap grows faster than light can make progress across it. Light still moves at the speed of light, locally, faithfully, and stubbornly. But the distance it must cross grows faster than its ability to cross it. The horizon is not a wall. It is a mathematical consequence of the expansion history. This is one of the deepest reasons the question, will the universe stop expanding, is not just about the far future, but about the limits of what can ever be tested. If expansion continues and acceleration persists, then more and more of the universe becomes causally disconnected. Distant galaxies fade from view, not because they turn off their lights, but because their light is stretched and diluted, and eventually because the light can no longer reach observers at all. Even before galaxies cross a strict event horizon, their light becomes harder to detect because of cosmological redshift. As space expands, the wavelength of light grows. The energy per photon decreases. The same source appears dimmer and redder. Over immense times, light can be stretched out of the visible range into infrared, then microwave, then longer wavelengths still. This means that, in practice, the observable universe is constrained not only by horizons, but by the sensitivity of detectors and the background noise environment. A source can be technically within reach of light travel and still become effectively invisible because its photons are too stretched to stand out from the cosmic background. The cosmic microwave background itself illustrates this. It is a powerful piece of evidence for the early universe because it is bright enough, in microwave terms, to measure precisely, and because its tiny temperature fluctuations contain rich information about density variations, geometry, and cosmic composition. But in the far future, if acceleration continues, the cosmic microwave background will be redshifted to longer wavelengths and become colder and fainter. Given enough time, it could become extremely difficult to detect. The universe would still have an early history, but future observers might have fewer accessible clues left in the sky. This is not speculation about psychology, it is physics. In an accelerating universe, information is lost from view. The cosmos becomes more isolated, not only structurally, but observationally. The question then becomes not only what is true, but what can be known. Some limits come from horizons. Other limits come from the fact that the universe is messy. Galaxies evolve, stars form and die. Dust absorbs and scatters light. In measuring cosmic expansion, astronomers have to untangle these local complications to extract the clean global signal. That is why cosmology relies on many independent probes, because no single probe is immune to every systematic uncertainty. This is where the modern toolkit of cosmology becomes important, not as a list of gadgets, but as a strategy for truth. Type 1. Supernovae provide a measure of expansion history through standard candle distances. Cepheid variables calibrate the local distance ladder. Baryon acoustic oscillations provide a standard ruler in the distribution of galaxies, a leftover imprint from sound waves in the early universe's plasma. Weak gravitational lensing reveals how matter is distributed by measuring subtle distortions in the shapes of background galaxies. The cosmic microwave background, mapped by missions like Planck, anchors early universe conditions. Each method has its own vulnerabilities. Together, they cross-check one another. Modern surveys do this at scale. The Sloan Digital Sky Survey has mapped millions of objects, helping establish large-scale structure and baryon acoustic oscillation measurements. The Dark Energy Survey used the Dark Energy camera to study galaxy clustering and weak lensing. The Dark Energy Spectroscopic Instrument, known as DESI, measures galaxy redshifts to map the expansion history using baryon acoustic oscillations and redshift space distortions. The European Space Agency's Euclid mission is designed to measure dark energy and cosmic structure with precision through weak lensing and galaxy clustering. The Vera C. Rubin Observatory, with its legacy survey of space and time, will repeatedly scan the sky, discovering vast numbers of supernova and mapping changes over time. These projects are not redundant. They are layers of evidence designed to protect cosmology from fooling itself. even with all that machinery and care, the universe keeps one more secret that matters deeply for the question of stopping. The cosmos is not just expanding. It is expanding in a way that depends on what it contains. And one of those contents, dark energy, is still not understood at a fundamental level. It is measured, its effects are clear, its nature is unsettled. That means cosmology can say with confidence what the data supports, while also admitting what remains an open problem. So what does the data support right now when it is seen through multiple independent lenses? First, the universe is very close to spatially flat on large scales. Planck's measurements of the cosmic microwave background strongly support this. Flatness means the total energy density of the universe is extremely close to the critical density. That is not merely an aesthetic claim. It is a quantitative one that emerges from the observed angular scales of features in the background radiation. Second, ordinary matter is only a small fraction of the total energy density. Most of the universe is not made of atoms. That conclusion is supported by multiple observations, including the relative heights of acoustic peaks in the cosmic microwave background, and the distribution of large-scale structure. The ordinary matter fraction is around 5%, meaning that stars, planets, gas, and everything built from protons and neutrons make up only a small slice of the cosmic budget. Third, dark matter is real in the sense that the universe behaves as though it exists. Galaxy rotation curves, gravitational lensing, cluster dynamics, and structure formation all point to a non-luminous mass component that clumps and provides gravitational scaffolding. Dark matter makes up roughly a quarter of the total energy density. It is central to building the cosmic web. Fourth, the expansion of the universe is accelerating. This is supported by Type 1a supernova surveys, by baryon acoustic oscillation measurements, and by the combined consistency of the cosmic microwave background with late-time structure growth. The acceleration is not guessed. It is inferred from the way distance relates to redshift across cosmic time. Fifth, the simplest explanation for acceleration is a cosmological constant, meaning a dark energy component that remains constant in density and exerts negative pressure. The equation of state is measured to be consistent with this within uncertainties, using combined constraints from supernovae, galaxy surveys, and the cosmic microwave background. Taken together, these points form the standard model of cosmology, often called the lambda cold dark matter model. Lambda refers to the cosmological constant. Cold dark matter refers to dark matter that moves slowly compared to light in the early universe, enabling structure formation in the observed way. This model is not treated as sacred. It is treated as the simplest model that fits the largest set of evidence at once. Now return to the question at the heart of the video. Will the universe ever stop expanding? Under the lambda cold dark matter model, the answer is no. Expansion does not halt. It does not slow towards zero in any meaningful finite time. Instead, the expansion rate approaches a behavior dominated by the cosmological constant. Matter density continues to dilute as the universe expands. Dark energy density stays roughly constant. That means the relative influence of dark energy grows with time. If dark energy remains constant, gravity from matter becomes less able, not more able, to reverse expansion. The universe becomes increasingly dark energy dominated, and expansion continues. This is not a claim of absolute certainty about eternity. It is a statement of what follows from the measured parameters. It is a conditional statement grounded in evidence. If dark energy behaves as a cosmological constant and remains so, expansion continues indefinitely. And this is where a careful, calm distinction matters. Cosmology can measure the equation of state of dark energy within the accessible cosmic past, because supernovae and galaxy surveys look back in time. It can constrain whether dark energy has changed significantly across billions of years. Current data suggests it has not changed much, if at all, within the level that can be detected. That supports the cosmological constant interpretation. But whether dark energy remains constant over trillions of years is not directly observed. It is inferred by extending the simplest model forward. This is one of the places where scientific language must be both firm and honest. The best supported model predicts continued expansion. No data currently indicates a coming slowdown that would lead to a halt. If anything, the evidence favors either steady acceleration, consistent with a cosmological constant, or a behavior very close to it. That is the current best answer. The main ways expansion could stop are also clear in principle, and they all involve a change in the physics as currently measured. Dark energy would need to weaken drastically, or reverse in sign, or be replaced by a component that allows gravity to regain dominance on cosmic scales. Alternatively, general relativity would need to be modified in a way that changes late-time expansion while still matching its successes in gravitational lensing, the timing of binary pulsars, and the gravitational wave observations made by LIGO and Virgo. None of those conditions is supported by current evidence. The universe also imposes a kind of observational patience. Some changes would be subtle and would require extremely precise measurements to detect. That is part of why future surveys matter. Euclid, Rubin, and Deci aim to refine the measurement of dark energy's behavior and the growth of structure. If dark energy is not exactly constant, deviations might appear as small shifts in the expansion history or in how structures grow under gravity. Weak lensing maps, for example, reveal how mass clumps over time. If dark energy evolves, it can change the rate at which structure formation slows. Baryon acoustic oscillations provide a ruler to track distances across redshift. A subtle deviation from the cosmological constant case could appear as a mismatch between predicted and observed distances. But that is the point. Cosmology is not waiting passively for the universe to reveal itself. It is actively building tests. The reason the standard model is trusted is not because it is pretty. It is trusted because it survives those tests so far. There is also a small, strangely human irony in all of this. The farther into the future an accelerating universe goes, the harder it becomes for any observers to reconstruct the full cosmic story. Acceleration pushes galaxies beyond reach. It dims the background radiation. It hides the evidence of expansion itself. In the far future, a civilization living in the remnants of a gravitationally bound galaxy might look out and see a quiet sky with no visible galaxies beyond their own. They might conclude the universe is static simply because the evidence has slipped away. That does not make the universe static. It makes the universe private. And in a way, that returns the question to its simplest form. Expansion is not a temporary phase like a gust of wind that dies out. It is the behavior of space-time under the influence of its contents. Right now, those contents include a dominant, smooth component consistent with a cosmological constant. That component drives acceleration, creates an event horizon, and tends to isolate the universe into separated regions over time. So, within the best supported evidence and the most conservative interpretation of that evidence, the universe does not appear to be heading toward a stop. It does not appear to be slowing into rest. It appears to be continuing, with the expansion rate shaped by dark energy, and with the future increasingly defined by horizons and by the gentle thinning of matter's influence on cosmic scales. The universe may still hold deeper physics in reserve. The vacuum energy problem remains unresolved. Quantum gravity remains incomplete. The Hubble tension remains under scrutiny. These are real open questions, but none of them currently point to a universe that is preparing to stop expanding. They point to a universe that is still being understood, not a universe that is changing its mind about its direction. And that is perhaps the calmest and most unsettling conclusion so far. The universe expands. The expansion accelerates. The limits of observation get tighter with time. And if the simplest reading of the data is correct, the expansion does not end, not with a halt and not with a reversal, but with an ever-stretching space-time that steadily carries the observable cosmos toward greater distance, greater isolation, and a kind of quiet that is written not in silence, but in geometry. As the universe continues to expand, the story stops being about how it began and becomes more about what expansion does, slowly, patiently, and with no need for drama. The most immediate effect is separation. Not separation inside galaxies where gravity holds stars in stable orbits, but separation between the large islands of structure that are not bound to one another. The cosmic web, with its filaments and clusters and vast voids, is real, but it is not permanent in the same visible form. In a universe where dark energy behaves like a cosmological constant, expansion accelerates in a way that steadily reduces how much of that web can remain in contact. Clusters of galaxies remain bound internally. The gravity of a massive cluster is strong enough to hold its galaxies together against the large-scale expansion. The same is true for smaller groups, like the local group. But on scales larger than those bound systems, the distance between clusters grows. Over time, clusters slip beyond one another's ability to exchange light, particles, or influence. It is not that space becomes empty. It is that the connections between far regions become thinner, then finally break in the only way physics allows, through causal separation. That causal separation is shaped by the cosmic event horizon. In an accelerating universe, there is a finite distance beyond which light emitted now will never arrive. The horizon is not a boundary that objects hit like a wall. It is a limit on communication. A galaxy can remain visible for a long time as its light was emitted long ago and is still arriving. But as the universe ages, new light from that galaxy becomes increasingly stretched and delayed. Eventually, no new signal arrives. The galaxy does not blink out in a single moment. It fades into irrelevance. Its photons spread into longer wavelengths and lower energies until they are swallowed by the background. Then, beyond the strict horizon, even in principle, nothing new from that region ever reaches an observer again. This means the observable universe changes with time, even if the universe itself continues. In the far future, an observer in a gravitationally bound galaxy could look out and see fewer and fewer external galaxies. The sky would slowly empty, not because those galaxies cease to exist, but because the geometry of space-time prevents their late light from ever arriving. The universe becomes, in effect, more private as it expands. Inside a bound region, time keeps doing what time does. Galaxies collide and merge because they are not isolated points. They are embedded in halos of dark matter and threaded by gravity. The Milky Way and Andromeda are expected to merge in a few billion years, forming a larger, more spheroidal galaxy. That merger does not resemble a crash in the everyday sense. The stars rarely collide because the distance between stars is so immense. Instead, the galaxies pass through one another, their gravitational fields reshaping orbits, stirring gas, triggering bursts of star formation, and then settling into a new equilibrium. After that, the galaxy remains bound, but it is also running out of youth. Star formation has already been declining in the universe for billions of years. Gas is not created freely. It is recycled, consumed, heated, expelled, and locked away. In the long run, the universe becomes less efficient at making new stars because the supply of cold, dense gas becomes harder to maintain. Massive stars burn hot and fast and die early. Smaller stars burn slowly. The most common stars, red dwarfs, can shine for trillions of years, which is hundreds of times the current age of the universe. In that era, starlight would still exist, but it would be dimmer on average, redder, and concentrated in fewer active regions. Eventually, even the slowest stars exhaust their usable hydrogen. The night sky inside the bound galaxy becomes dominated by remnants. White dwarfs cool, neutron stars spin down, and black holes become the most durable objects around, not because they are immortal, but because their clocks run on absurdly long timescales. Neutron stars are the compact remnants of massive stars, held up by neutron degeneracy pressure and nuclear forces. Many are born spinning rapidly and radiating beams as pulsars, first discovered by Jocelyn Bell Burnell in 1967. Over time, their rotation slows. Their magnetic fields evolve. They become quieter. They can still exist for enormous lengths of time, but their activity fades. White dwarfs are the remnants of sun-like stars, supported by electron degeneracy pressure. They begin hot and then cool slowly, radiating away their stored thermal energy. In the far future, they become cold, dark objects, sometimes called black dwarfs. Though that term refers to a hypothetical final state that the universe has not yet had enough time to produce. Cooling times for white dwarfs can be extraordinarily long, extending far beyond trillions of years, depending on the details of their composition and environment. Black holes sit at the far end of this chain. They grow by swallowing gas, stars, and sometimes by merging with other black holes. Observations by the LIGO and Virgo collaborations have shown that black holes merge and release gravitational waves, ripples in space-time predicted by general relativity. The Event Horizon Telescope has imaged the shadow of a supermassive black hole, revealing a ring like glow shaped by gravitational lensing. These are not abstract objects. They are real, and they are common. Yet black holes also present one of the most haunting predictions in theoretical physics: Hawking radiation. Stephen Hawking argued that quantum effects near the event horizon allow black holes to emit radiation, losing mass over time. This is not a classical process. It is rooted in the uneasy marriage between quantum field theory and curved space-time. The smaller the black hole, the faster it evaporates. A stellar mass black hole would take a time scale on the order of a 1, followed by about 67 zeros of years to evaporate. A supermassive black hole would take longer still, on the order of a 1 followed by about 100 zeros of years. These timescales are so extreme that they do not function as narrative in the ordinary sense. They function as perspective. They show that the universe's long future is not measured in eras like human history. It is measured in numbers that dwarf every familiar scale. If Hawking radiation is correct, then even black holes are temporary. Over those vast spans, they evaporate into low-energy particles and photons, and the universe becomes a thinner and thinner bath of radiation, drifting toward thermal equilibrium. If dark energy remains constant, expansion continues throughout, spreading that remaining energy across an ever larger volume, lowering temperature toward an asymptote. The Big Freeze, or heat death, is not a single moment but a direction, an arrow, a steady thermodynamic slide toward maximum entropy. At this point, the fate of structure and the fate of observation become tangled. When energy is spread thin enough, new complex processes become rare. When galaxies are isolated by horizons, the wider universe becomes inaccessible. In principle, the universe could still contain vast regions full of galaxies and activity far beyond any local view, but those regions would be causally disconnected. They would exist without being able to share their existence with one another. This is one of the most important ways to understand the future of an accelerating universe. It is not just that things get farther apart. It is that the concept of the universe becomes locally defined. Each bound region becomes its own island, carrying its own history forward without access to the rest. The universe does not end. It becomes unshared. There are, of course, alternative possibilities, and they remain worth stating plainly without turning them into suspense. If dark energy is not constant, then the future could deviate from this path. If dark energy weakens over time, acceleration could slow. If it fades enough, the universe could return to a matter-dominated expansion that decelerates, though that does not automatically lead to a halt. If dark energy strengthens in the phantom energy way, the future could include a big rip, where bound structures are eventually torn apart. If dark energy changes sign, or if gravity behaves differently on the larger scales than general relativity predicts, recollapse could become possible in some models. But the best current evidence does not require those alternatives. Measurements of the equation of state of dark energy are consistent with a cosmological constant. The cosmic microwave background mapped by Planck strongly supports a universe close to spatially flat. Supernovae observations indicate acceleration. Large-scale structure surveys support the same basic parameters. The simplest consistent model remains the lambda cold dark matter model. With that model in mind, the original question becomes almost oddly calm. Will the universe ever stop expanding? Under the best supported parameters, no. Expansion does not drift toward stillness. It does not slow to a halt and wait politely for gravity to pull everything back in. The reason is not a lack of gravity. Gravity remains powerful locally, shaping galaxies, clusters, and stellar remnants. The reason is that the dominant component shaping large-scale expansion appears to be dark energy with negative pressure, behaving like a cosmological constant. As the universe expands, matter dilutes. Dark energy does not. That means the component driving acceleration becomes more dominant over time, not less. So the universe is not headed toward a natural stop. The universe is headed toward continued expansion, continued horizon formation, and a future where more of the cosmos is lost from view. The most likely ending, if the word ending is even fair, is not a crash or a collapse. It is a slow thinning, a steady dimming, and a deepening separation between regions that can no longer touch. There is a quiet irony in that. The most dramatic cosmic discovery of the last century, that the universe is accelerating, points toward a future where evidence becomes harder to see. A far future civilization living inside a merged galaxy long after external galaxies have slipped beyond the horizon might look out and see only their own island of stars. Without the cosmic microwave background being easily detectable, without distant galaxies visible, without a sky full of redshifts to measure, that civilization could conclude the universe is static, simply because the universe has expanded itself beyond what they can observe. The cosmos would not have become static. It would have become observationally lonely. And that is perhaps the most useful way to hold the original question in the mind. The universe is expanding, and it is doing so in a way that reshapes what can be known. The expansion is not merely motion. It is the changing geometry of space-time. It is the stretching of wavelengths. It is the creation of horizons. It is the long-term redistribution of energy. It is the slow movement toward a state where gradients fade and structure becomes rarer. So the answer, grounded in what is measured rather than what is wished for, is that the universe does not appear to be heading toward a stop. If dark energy remains close to a cosmological constant, expansion continues indefinitely. The future is not a final breath that runs out. It is a long, quiet exhale that never quite finishes, carrying the universe into greater size, greater separation, and a calm emptiness shaped not by destruction, but by distance. If anything remains truly unsettled, it is not whether the universe expands or whether it accelerates, but why the dominant component has the value it has, and whether it is exactly constant forever. That is where the boundary of knowledge sits right now. The map is clear. The underlying engine is still being understood. But even without that final understanding, the trajectory is plain. The universe expands, and under the best evidence available, it keeps expanding. Not toward a finish line, but toward a far future where the night sky grows quieter, the cosmos grows more distant, and the largest structures become memories written into light that is still traveling, still stretching, still fading as it goes.